let's go over the course syllabus now. Okay, I gave you the course syllabus, right? It's it's just one sheet. Yeah, printed on both sides. Okay, let's go over the course syllabus and make sure that literally we are on the same page. Okay. In other words, I want you to know exactly what you're expected to do, and also I want to let you know what you can expect from me. Also, the course content, this is most important. This is the most important thing. I'm going to tell you the grading policy as well. This is modern physics, quantum mechanics. We start at 1310, not at 13. Okay, and we go until 1430. Right? And this is my name in kanji. My name in kanji is, in Japanese ideographs, this is my name, Masayasu Aotani. What do you call me? I don't know. In the States, they called me Mr. A because both Masayasu and Aotani was awkward for them. So you can call me Mr. A, or if you can pronounce it, you can call me Masayasu or Aotani, either way. My email, here is my URL, phone number, and you have a question. If you have a question, the best thing to do is to call me, okay? I almost continually, I read my email through, but if you have a question, the best thing to do is for me and for you to do is to answer it, to ask and answer it interactively. You see, the problem with an email is that so often, I or you misunderstand what's written, and then we have to go back and forth, and that's kind of tedious. If it's a phone conversation, you see, as soon as I started answering a wrong question, then you can correct me, you can stop me, and tell me what you're really asking and stuff. So it's more efficient, more effective and efficient. In pursuit of efficiency and effectiveness, call me. Don't send me email. And call me means call me on the phone. Okay, don't knock on the door. Unless you have an appointment. This is because of my field, I think. Math and physics, it requires like really undivided attention and very strong concentration. So I'd rather not be disturbed. Let's see. Prerequisite for the course is this. You should be familiar with the fundamentals of Newtonian mechanics. Means, by this I mean high school physics, okay, at that level, Newtonian mechanics. And you should know basic calculus. So you should know what differentiation and integration means at the high school level. That's the prerequisite. And I gave you the first batch of our course notes, but that's only, let's see, the course notes are about 350 or 60 pages long, and it is very thorough with lots of, as I say here, let me read it. Our course notes are very thorough and contain many asides, digressions, and extras, as well as advanced materials. And my lecture covers only about, 1/10 of what's, in the course notes. So what you should do is to save it, to save the course notes for future reference, And I made sure that the kind of stuff, the kinds of things that I had difficulty with when I was learning quantum mechanics, and also elementary mathematics needed to understand quantum mechanics. I tried to explain all those things in my lecture notes, so you'll be grateful later in your life if you don't throw it away and save it. Okay, as I say here, my lecture will be a watered down made much easier. That's what it means, watered down version of the course notes. Occasional handouts. From time to time, I give you oftentimes handwritten handouts, and they are more down to earth with concrete examples. So the point is, the reason why I'm spending so much time talking about the course notes is simply that many of you, okay, come to the class and look at the course notes, or on the web. You see, it's available on the web. Look at the course notes on the web and see that it's almost like a graduate school material. That's true. If I did everything there, that's good for graduate students, but that's not what's going to happen. The actual lectures are going to be much easier. Speaking of the course notes, by the way, I want to let me bring to your attention one feature, very simple feature of the course notes. Okay, here is the course notes, right? Okay. If you download the course notes from the web, right, then you have the kind of features I'm using here, like bookmarks and stuff. And what I'm trying to show is, let's see. What you should read is, this is an important okay, an important feature of these course notes. What you should read is text like this, and on your first reading, you should skip all the shaded, just glance at them, but skip all the shaded regions. There are quite a few much later. At this point, since this is chapter 2. Chapter 2 is mathematical preliminaries. You don't have that many blue, shaded areas, but later on there will be quite a few, and you should skip all of them. For example, skip this, right, and skip this. Just glance at them, so you'd know what it looks like, but skip these, and so on, right? These are more advanced materials, or sometimes these are sort of digressions, you see. So at your leisure, you may want to look at them later, but not now. Let's go back to the course syllabus. So that's course notes. Homework. There will be weekly assignments of 3 to 4 problems on each homework set, except for the first and last week. So there is nothing this week. This is for your understanding only, and oftentimes answers are already posted on the web, so you do not have to turn them in. You don't have to turn them in. However, this is an important however, some or all of the problems on the final examination will be similar to these problems, okay? So it is, to your advantage, you see, to take the homework problems seriously. They are given as assignments because they are important issues, and important points in elementary quantum mechanics. Examination. There will be an open notebook and open lecture notes final examination. What it means is that if you have your own, note, in other words, if you take notes during the lecture, you can bring it in, and also the lecture notes I give you, okay, the lecture notes I give you during the class, you can bring them all in. In other words, you don't have to memorize, like formulas and stuff. That's totally unnecessary. But this is important. Please note that the only materials you can use during the examination are your notes. You see, your notes. And also my means the instructor's distributed lecture notes. and also your own handwritten solutions to homework assignments. You can't bring in copies of other people's like handouts or other people's solutions. Right? So that's another reason. That's one good reason why you should attend the lectures. You know? Let's talk about the course grades. So the final course grade. By the way, I'm an easy grader, if anything. Okay, here's my grading policy. The final course grade is based on the final examination. There's only one final examination, and grading policy is like so. I call this the lowest guaranteed grades, and I'm going to explain what this means, okay, in detail in a few minutes, but let me go over this first. If you get at least 80% on the final examination, or, this is or, okay, this is not and, this is or if you are in the top 1/3 of the class, then you are guaranteed a letter grade of A, okay? This is or again. So if everyone in the class gets 80%, say, for example, then I only give A's, correct? Because this is an or condition. Similarly, if you get 70% on the final, or if you're in the top 1/2 of the class, you'll get a B. And if you get 50% on the final, or in the top 90% of the class, you'll get a C. Now, as I said, this is the lowest guaranteed grades. What it means is that if you did these things, you are guaranteed A, B, the grades of A, B, or C, but I reserve the right to deviate upward. In other words, suppose it doesn't happen often because I have enough experience with this class, but suppose I made the final exam very difficult, say, you know, then the average may be like this is a fictitious, you know, situation, but the average may be only like 30 points, you see. When something like that happens, I freely deviate from this rule and give A's to those who I think, you know, deserve a good grade. So deserve good grades. So that's what I mean by the lowest guaranteed grades. Is the grading policy clear to you, including lowest guarantee stuff? Any questions? Yes? It's clear. Thank you. It's crystal clear, right? It's quantitative and it's crystal clear. Some professors give like very qualitative grading policy, you know, if I am satisfied with their progress. Ah, wow. Anyway. I do not usually fail many, but this is especially for Kyoto University students. But if you prefer a grade of F for various reasons, please let me know before I file an official score report. However, let me read the rest. This usually involves letting me know right after the final examination, meaning before I've graded the exam. Okay, so when you finish the examination, if you want to just, you know, cancel your score and you just want to fail the class, you can tell me that. It is not after you have had a chance to check your grades. No, it doesn't work that way. Okay, and also, yeah, also come to my office and give me a reminder. Okay, so the ball's entirely in your court. Okay, you have to hit it back and let me know what you want and make sure. You know, this is like double checking. you have to come to my office later and demand that I do what you asked me to do. Okay. By the way, just as an aside, if you are an international student, you may be wondering why someone might prefer a grade of, like B or F, not as opposed to B or C. And that's simply because at this university, you see, at this university, if you get an F, it doesn't show up on your transcript. It is the same as like you've never taken it, you see. So that's the system here. But that's not necessarily unfair because we don't have a GPA, So we only go by the number of units, credits each student has obtained, and they graduate after they accumulate a certain number of credits, and the average grade, even though they can be computed if you want to, that's not show up on the transcript. There is no concept. You see, at many schools in Japan, there is no such thing as a GPA. See, that's why. One more, attendance and in-class announcements. Attendance coming to the class will be, attendance will be taken at every lecture. Today, that lady, her name is Ike-san. Ike-san brought a attendance sheet, and it's taken every time. And some important announcements will be made during the lecture for sure. So please make sure you get them from other students if you have to miss a lecture. Don't come to me and ask me. Number one, I may not remember, and number two, it's an imposition on me because I showed up and you didn't. Okay. Ask your friends, and don't come to my office and ask me to explain everything I explained in the class just because you missed it. And also, we recycle very quickly. So if you miss a lecture and if you didn't get a handout, you have to copy it, you have to copy your friend's handout. Sometimes I have an extra copy, but our system is quite efficient when it comes to recycling, and so oftentimes, right after the class, I recycle. Registration, it is the student's responsibility to properly register for this class. You might think this is weird, right? This is not a grade school, and you may think it's weird, but the thing is, at least one student, in the past, 30 years of teaching, I guess, every year, at least one student, sometimes more, multiple, more than one students come to me and ask me to sign a special form so he or she can get credit. It's because that person did everything in the class, attended the class, took the final exam, everything except, registering for the class properly. So, make sure it doesn't happen to you. It's not an enjoyable experience. One final note. Well, maybe I shouldn't say most, but many Japanese college students and also many professors are jokers when it comes to attending classes and giving lectures. That's true, because traditionally, up until 20 years ago, professors were judged solely by their research and not their teaching whatsoever in this country. It's wrong, of course, but that's how it was. And since professors didn't teach well, students, those who wanted to learn, they had to go and study on their own. And because of that bad tradition, still many students are lazy and many professors don't teach well. But that's no reason why you shouldn't take this lecture seriously, because I, myself, just for a change, I guess, I take my teaching very seriously, just as seriously as my research. And I'm not one of those jokers. Therefore, you're expected to respond in kind. Okay? Any questions about the syllabus at this point? Everything is crystal clear, and you're sick and tired of my spiel, and you want to start learning physics. Yes? No? Yes? So if you come up with any question, even during the lecture, or also right after the lecture, during the lecture, raise your hand, and right after the lecture, you can come to the front and ask me. Okay. Physics. Let's start physics. Gone is the syllabus, and so I'm going to start from the beginning, which is page 13. Okay. Chapter 1. The title of chapter 1 is Classical Physics versus Classical Physics and Modern Physics, their comparison. Of course, what you learned in high school, well, at least in Japan, I don't think you learn quantum mechanics and relativity in high school, do you? In my days, I didn't. Did you learn it in high school? I suppose not. So high school physics is mostly Newtonian mechanics and some electricity and magnetism, right? Newtonian mechanics and electricity and magnetism. And everything was fine, with classical physics, classical theories, like Newtonian theories and Maxwell's electricity and magnetism. Until the end of 19th century, and also in the beginning of the 20th century, around that time, many problems surfaced with classical physics. Basically, up until then, until late in the 19th century, our technology, our ability to conduct experiments and our ability humans' ability to make precise measurements, right? They were not that good. And so small differences couldn't be detected. And also extreme phenomena, like, for example, like an electron, moving in an atom. You see very small microscopic phenomenon. Or some particle moving near the speed of light. That's an extreme phenomenon, right? They were not, within reach of experimental physicists. But those techniques slowly became available toward the end of the 19th century, and that's when they found difficulties, they found problems with classical physics. First, when they looked at things, objects which move at near the speed of light. Right? The speed of light, how fast it goes around the Earth, how many times? 7 or 8 times in a second. Right? And when a particle is accelerated to like 90%, 95%, 99% of the speed of light, its behavior was not what was expected, based on classical physics. And in order to explain those high-speed, phenomena, we needed relativity. We actually needed special relativity. There are two kinds of relativity, right? Special relativity, special theory of relativity, and general theory of relativity. General theory is a theory of, it's a geometrical theory of gravity. And special relativity helps us understand what happens when an object moves at near, the speed of light. On the other hand, people began to be able to observe like microscopic phenomena, like electrons. And they found that electrons are not quite like a baseball. Okay? Newtonian mechanics, a typical baseball, a movement of a typical baseball, a car, anything, a plane, can be explained perfectly. Perfectly means within measurement error, but perfectly, as far as experimental physics is concerned, those phenomena could be explained by Newtonian mechanics. But movement of electron and the things, things means, I'll come to it in a few minutes, okay? The kind of things, the behavior, electrons and other small particles were exhibiting was nothing like what we would expect from Newtonian mechanics. And speaking of small particles, here is another thing. Those particles were not quite particles. See, a baseball is a baseball, right? A baseball is a baseball, you can grab it. But an electron is not like an extremely small baseball. It's not like that. So in summary, to explain high-speed phenomena, we needed relativity, special relativity. That's one branch of modern physics. And to explain microscopic phenomena, like subatomic particles, right? We needed quantum mechanics. The advent of quantum mechanics, the first sign of problems with classical mechanics or classical theories was what is called black body radiation. A black body, I have a nice graph. Nice graph. This is a graph of black body radiation. A black body is it's an idealization, okay? In physics, when we say a black body, it does not just mean something that's black, like so, but an ideal black body is something that does not reflect any light. No light is reflected from the surface. So if reflection is the only thing there is, then we can see a ideal black body, right? But luckily, anything with temperature, okay, anything with a non-zero temperature would radiate, an electromagnetic wave, and you can make that measurement. Now, if you measure the radiation as a function of, as you can see here, as a function of, I'm looking at figure 1.1, okay, as a function of temperature and wavelength, then this is the temperature of the black body. You see, it doesn't reflect any light, but it still emits light. This is classical theory, according to the classical theory. what they actually observed was nothing like this. You see, this is just like climbing, monotonically, increasing, correct? But you see, these are humps. They observed humps. How come? Classical theory predicts this. They observed this. It's obvious something's very wrong with the classical theory. And in order to reconcile, and solve this problem, Max Planck, a German physicist, Max Planck came up with the idea of quantization of energy. What it means is, without going into math, qualitatively, okay? For a while, my presentation is going to be heuristic, storytelling type, because experimental details are too cumbersome. So also mathematical details are also, we don't want to get bogged down, worrying too much about the details, mathematical details. So here is the difference between classical physics and Max Planck's idea. In classical theory, okay, again, my presentation is going to be heuristic, but in classical theory, energy is continuously distributed. In other words, just think of, for example, think of a kinetic energy of a car. Okay, when the car is in a standstill, when it's not moving, the kinetic energy is 0. Right? As it starts moving and it keeps accelerating, the kinetic energy is 1/2 mv squared. And since as the speed increases, as the speed increases, of course, the kinetic energy also increases and continuously, right? There is no such thing as the velocity going from 5 to 10, 10 to 15, nothing in between, right? But, so the picture should be, the classical energy distribution picture should be, here is your energy. It's just anything, any value is possible. Max Planck said, no, actually what you can have is discrete energy levels. Discrete energy levels. And the measure of these gaps is represented by a constant called Planck's constant. Now, his assumption, according to him, this h, this constant, is 6 times 10 to the minus 34. It's just a second, please. Here we go. Okay, this is, I'm on page 15 of the lecture notes, and this is Planck's constant. And as you can see, 10 to the minus 34. So you can understand what's happening. Here is a classical picture, continuous. Here is Max Planck, discrete, gaps, 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 but it's 10 to the minus 34. You see, that's how large these gaps are, so to speak. Therefore, physicists prior to that time, I'm talking about the end of the 19th century and the beginning of the 20th century, they weren't able to detect a small difference like this. That was his assumption. And he said there is a connection between the energy and frequency, and the relation is E is equal to h times nu, where nu is the frequency. Okay, You see, he was looking at electromagnetic wave. And h is like of the order 10 to the minus 34, extremely small. So this was his postulate. This is a big jump, right? Because if you are only concerned with like macroscopic phenomena, like our running or waters, running water and stuff like that, an airplane, whatnot, it's obvious things are continuous, isn't it? Correct? But somehow, to explain what was observed, it was necessary to assume this. So this was the first sign of a problem. One of the first signs, say. After Max Planck, by the way, I have to make a correction. This is Planck. This is correctly spelled Planck. It's misspelled here. C is missing. Okay. I've already corrected it. So if you look at the online notes, Max Planck, Planck is spelled correctly, but P-L-A-N-C-K. By the way, if you talk to either here in Japan or in the United States, if you talk to old physicists, old school guys like those who are in the 70s and 80s, you see, they say, they don't say E equals h nu. They say E equals ha nu, because Max Planck was German, and German H is pronounced ha, and it was in honor of, I guess, his insight. But for us, it is h nu. Then came Einstein. Okay. Einstein was familiar with this, Max Planck's idea. And then he tried to explain what is called a photoelectric effect. A photoelectric effect was something like this. If you have a metal, it can be a metal block, it can be a thin plate of metal, I guess. But if you have a metal surface, I think they use nickel first, I believe. Maybe I'm wrong. No, wait a minute. Scratch it. I'm not sure. Metal plate, and when light shines on it, an electron is ejected. Okay. That much is fine. It simply means the energy, the light ray, the ray of light possessed, it was transferred to this electron, and the electron has a large kinetic energy, motion energy. Therefore, it just jumped out of the metal. So far, so good. But a weird thing happened. Okay, a classical picture from here on, it is extremely heuristic, but I think it's easier to understand it this way. Now, the classical picture was something like this. You see, it's a metal. So metal atom, the nucleus is positively charged, and an electron is bound to, even free electrons are really bound, right? That's why they don't come out of the metal. So our heuristic picture is something like this. Okay, here's an electron bound to this metal, and the classical picture is light. It's a wave. Light wave shines here on this system and sets the electron in motion, and slowly, as light keeps shining, this amplitude gets larger and larger and larger, and finally the electron has enough kinetic energy, so it breaks away and it comes out of the surface. Now, with this view, you don't need a very energetic, strong light. What you need is, even if the light is weak, if you keep shining for a long time, say, do it for 2 hours, then eventually an electron should come out. But as it turned out, there was a clear threshold, energy threshold for the light in order to observe an ejected electron. In other words, if the energy level is too low, the light wave's energy is too low, no electron was observed. And that contradicts our classical view. So Einstein said, maybe that's not what's happening, but what's happening is something. I'm going to erase it and draw it again. What's happening is something like this. It's plus. Here's an electron. And what's happening is light is not quite like this, but it is bundles of energy. In other words, energy is concentrated in localized, in a very short area. Now, if such is the case, what happens is, if this guy hits the electron, and if this has enough energy, this guy has enough energy, then an electron is ejected. But if it doesn't have enough energy, then it may set the electron in this vibratory motion just a bit, but then by the time the next bundle arrives, this motion has subsided. So, the next guy hits the electron again, a small motion. The next guy, by the time the next guy arrives, this small motion has been damped, and with this view, this view was consistent with what was being observed. And so he said, as a postulate, he said, we don't have light waves, we have light particles called photons. Now everyone's familiar with the term photon, but in those days, regarding light, not as a wave, but as a bunch of, particles, that was quite novel. And since Einstein already knew Planck's success, he also said each photon has this energy, and each photon, this comes from special relativity, by the way, each photon has this momentum. But looking at this, you see there is something weird going on here. It's a particle, right? It's a bundle of energy. Then, how come? How come Einstein, or these formulas, they refer to frequency nu and wavelength lambda? Why? It doesn't make sense. On the other hand, if it's a wave, then photoelectric effect could not be explained. So, to reconcile, to resolve this situation, there was only one thing to say, and that was what is now known as wave-particle duality. Wave-particle duality. Now, if you look at yourself, it's an object, it's a bunch of particles put together, and it just doesn't really seem like I'm a wave also, right? But in the microscopic world, photon is no exception. Wave-particle duality was reality, you see? So physicists were beginning to feel that, beginning to see that definiteness of Newtonian mechanics, you see, something is either a wave or a particle, and was not quite right. As pleasing as it was, say, to your brain, conceptually it's pleasing, but that's not right. By the way, the reason why you feel that it's weird that something can be both a wave and a particle, it's simply because we aren't microscopic particles, you see? If we were electrons and we were photons, that is our reality. If someone says, which one are you? You go, what do you mean? I'm both, okay? So physics is an observational science. So whatever theory can explain, experimental results, observations, that is by definition, so to speak, by definition, that's the correct theory. Now, at this point, by the way, Einstein was only talking about photons. But then came another guy came to the scene. His name was Dubois. Pronunciation is many speakers of English say Broglie, but Dubois. Dubois came about and said more or less what I just said. It's not just photon, it's not just light, but generally speaking, things are, what we think are objects, are particles. Generally speaking, they are, everything's both a wave and a particle. And he said, even what we consider a matter is not a wave, a matter is matter. Even we consider a matter has wave property that can be explained by these two formulas. So these are exactly what Einstein, postulated for photons, and now Dubois extended it, so to speak, generalized it to other particles, like an electron, for example. And what did I just say? I said physics is an experimental science, so whatever can be confirmed, experimentally, is correct, right? So whatever theory that can be confirmed experimentally is correct, and indeed, this wild and wacky theory was confirmed here. See, the correctness of these formulas was soon confirmed by two American physicists, Davison and Germer. So let's take a deep breath and let me summarize, what we talked about so far in this lecture, in terms of physics. Classical physics, right? Newtonian physics and Maxwell's electricity and magnetism. It turned out there were problems. In other words, there were many experimental, many observations that could not be explained by classical theories, or that did not agree with classical expectations, predictions made by classical theories. There were two arenas. One was high-speed phenomena. The other was microscopic phenomena. One is real fast. The other is really small. Electrons, light. Okay. And in order to resolve the problems physicists encountered, for the objects moving at near the speed of light, we needed relativity, special relativity, and in order to account for microscopic phenomena, like what electrons, photons, those guys are doing we needed quantum mechanics. And quantum mechanics, unfortunately, we have only so much time, so we are not going to talk about special relativity. We are going to concentrate on, only on quantum mechanics. But in quantum mechanics, already two very important concepts emerged. Number one, energy level is quantized. Energy level is discrete. It's not continuous. Okay? And the measure of discreteness, the measure of the gap, is the Planck's constant, Planck constant h. H is of the order, it's something like 6.6 times 10 to the power of minus 34, so it's extremely small, joule seconds. That's one thing. Okay, two important concepts. One is discrete energy distribution. By the way, I use two expressions interchangeably. Sometimes I say energy levels are discrete, and at other times I may say energy is quantized. Right? They mean the same thing. And number two, particles aren't particles, and waves aren't waves. Waves aren't waves. Why? Because light sometimes behaves like particles, photons. And why particles aren't particles? Electrons. Electrons sometimes behave like a wave. This is called wave-particle duality. So we need to associate, in quantum mechanics, we need to associate waves to physical objects. And that's we will do for the rest of this course. And basically, what you're going to do is to come up with a differential equation. And the solution of that differential equation gives you a wave. Okay, it works like that. By the way, if you still aren't convinced, I would say you almost shouldn't be. You aren't convinced that electrons are sometimes they behave like waves. There was an experiment roughly like this. Okay, this is a rough sketch of that experiment. An electron beam, see, electron beam, okay? And here's an opening, two openings. These are called slits, two slits. And a detector screen here, right? Detector. And they detected, they observed where, these electrons, this electron, where it hits, where on this detector plate the electron hits. And you'd expect, well, classically you'd expect, if this is a narrow slit, you'd expect maybe a lot here and a lot here. And maybe some are coming at an angle, right? So maybe something around here, something. But mostly here and here, right? True. That's what you'd expect. But what they observed, when they actually conducted this experiment, what they observed was something like this. I'm going to redraw it, okay? They observed what they observed was the length means how dense, how thick it is. They observed the pattern like this. What the hell? Doesn't make sense. See? Doesn't make sense it doesn't make any sense of any kind. And the reason was electrons were behaving like waves. In other words, wave, wave, wave. If they were like waves, okay? Think of a typical wave, like if you throw a stone into a pond, then you form, you have like traveling waves, outward from where the stone entered the pond, and it moves outward in concentric circles, right? Yeah, in that pattern. And if it was not a particle beam, but if it was a wave, what it does is when it encounters a slot, it does this. This is what a wave does, right? Okay. This is what a wave does. And sure enough, they interfere. Two waves interfere. Sometimes, just think of a sine wave. Sometimes this wave, their crest, their crests, they coincide. Therefore, it is a wave twice as large. Sometimes you have one wave negating the other wave, which is just like so. See? This is dead zero here. The amplitude is 0, like so. So this interference pattern is perfectly consistent with the wave assumption, wave nature of electron. And something like this can never be explained with a particle view. So this is reality. Again, the reason why, you see, the reason why we feel it is, so surreal or unreal or whatnot, sci-fi, say science fiction, is simply because we aren't electrons. If we were electrons, this is our daily occurrence. Since we don't have an opportunity to come back to this high speed, like special relativistic phenomenon, I want to I want to talk about an exciting development in that arena. Okay, this is Kyoto, right? Right next to Kyoto is Osaka, but also, if you go north, next to Kyoto is Hyogo Prefecture. See, that's how these three prefectures, Kyoto, Osaka, and Hyogo prefectures are located. And in Hyogo Prefecture, there's a thing known as sakura. Japanese people say sakura, however, the spelling is S-A-C-L-A. Which stands for something. Okay, it takes a while to explain what it is, but it stands for spring 8 angstrom, compact, free, electron, laser. Anyway, what this does is, what this really is this is I'm not sure. Accelerator. Is this correct? I suppose. It's an accelerator, and also it's a microscope. It is. It accelerates electrons and bends its path. And when an electron's path is suddenly bent, which is the same as it's an electron moving along the straight line, all of a sudden experiences a strong acceleration, right? Change of direction is also acceleration. When it happens, it emits light, and that light is used to see very tiny things, such as, this is true, such as one atom. Now, how fast is this electron, are these electrons they are using as a microscope? They are all 0.9999999 C. So this is how far our technology has gotten. So this is like 99.9999 99.999999% of the speed of light. That's how fast it is. And how about the light? How about the light it produces, when you can accelerate an electron? An electron is really small, right? If it hits you, nothing happens, you don't feel a pain or anything. But if it is accelerated up to this speed, the light you get from this electron is it is 10 to the 16th times something. What is it? What do you think goes in here? Sunlight. Okay? So we are beating the sun, beating the sun to the punch easily. So you see, special relativity and also high-speed phenomena is extremely important, and it's actually generating results. It was like, was it 2012? A couple of years ago, someone found a molecule that served as a catalyst for photosynthesis, because now you can see each atom. So you can certainly see a molecule, correct? So that's how exciting modern physics is. Let's see. Okay, I owe you just about 1 minute, but this is a good place to stop. So go home and read the notes and get excited. Okay, see you next week. If you have a question, come up. Otherwise, go home, or you can't go home yet. Yeah? Me neither.